This is Science 10, Law of Conservation of Energy lesson, part 1. Before you begin, check the srtpotionsmaster.weebly.com website, print yourself a physics data sheet and your Law of Conservation of Energy student notes. These student notes are what we will be working from today. They look like this, and it would help you to have a calculator, so pause the video. At any time, if you find the video is going too quickly for you to fill in your notes, just hit pause and fill in your notes and then resume. Okay, the first part of this is filled in for you about conservation of energy, just some informational that you can add to your notes. The place I'd like to start is question 1, which is law of conservation of energy, and that is energy can neither be created or destroyed, and the sum of all the energies in a system remains constant. So when we look at our conservation of energy equation, we do have an addition sign between potential and kinetic. That's the sum of the energies. And as a reminder, mechanical is NE, and mechanical energy in other equations and word problems is also referred to as total energy. So if you see the term total energy, sometimes it'll be TE over here to include in your equation. Okay, our pendulum picture has got an example of where we have max potential energy, which is at the start and at the end, its highest point. Zero potential energy, which is down here at the bottom. The pendulum in this picture is swinging this way. So at the very bottom, it'll have zero potential. If I switch to talk about max kinetic will be at the bottom. This is where our pendulum is going the fastest. And as it swings back up to the top, we'll have, again, maximum potential, its highest point, and zero kinetic because it will pause just for that split second before it swings back down. For questions 3 and 4, it talks about energy transformations in a roller coaster. I have filled these in for you, so if you want to pause the video, you can fill in your notes. And the same with question 5 here. The start of this coaster, when it asks you the highest point for potential energy, which is there, it's talking about starting here and then going down the first hill. So I filled in those transformations. I'd like you to try those on your own and then unpause your video and check your answers. Okay, here at number 6, the law of conservation of energy equation is written out in the long format for you. It looks like it has 4 separate terms. So just to review, the I's stand for initial, that's at the start of your ride, and the F's will stand for final. So on one side of the equation we have initial, the opposite side we have final. So 4 terms looks like it could be a fairly complicated equation. However, if we take a simple example, an object at rest at the top of a hill, if it's at rest at the top of the hill, its initial kinetic energy will be 0. So this term here can be crossed out of our equation. And as it rolls to the bottom of the hill, if it's at the bottom, its final potential will also be 0, and that removes this from our equation. This simplifies our equation to potential energy initial equals kinetic energy final, or potential energy at the top of your hill, if you're talking roller coaster, equals kinetic energy at the bottom. All that potential is going to be converted to kinetic. And number 7, we'll do an example with that. Have your data sheet in your calculator. As we read the question, we'll pick out the important parts. You're on a frictionless, air resistance-free coaster, paused at the top of the first hill. That tells you you're stopped at the top. Coaster is 22 meters above the ground. That's H in our variables, and weighs approximately 535 kilograms. That's M, or mass. How much PE do you have at the top? So we've used this equation a lot, so this will be a quick review. PE equals mgh. Fill in our variables, 535 for mass. Gravity is 9.8. Our height is 22 meters. If we put all this into our calculator, this is our answer. And it's energy, so we have to remember energy is always in joules. Our next piece of question asks how much KE will we have at the bottom, but it has given us no new numbers to work with. So we can't go solve for KE using our KE equation, but we do know that PE at the top is equal to KE at the bottom. So this amount of potential energy is all going to get turned to kinetic energy. So that becomes our answer for the second part of our question. And we don't need to do any extra solving. We just move our number of joules down. And our last piece, how fast will you be going? Well, fast is velocity in our variables, or V. So we're going to get our kinetic energy equation, KE equals 1/2 mv squared. And we're going to fill in all the variables we know in their right locations on either side of the equals. So the kinetic energy is this big number that we solved for in part A, 1/2, mass, which is 535. V squared is what I'm looking for, so I call it V. Now I have to move my algebra up here. I should have left a little more room. The first thing is this piece here, 1/2 of 535. You're going to do that in your calculator by doing 535 divided by 2. And our next line will be 115,346 joules equals 267.5 V squared. Now you're going to divide 267 by itself to cancel it like that. And on your calculator, you're going to divide the other side. And that is going to give you an answer of 431.2 equals V squared. Okay, just a reminder, this is a squared. You should be thinking that's a really big number for velocity. So we're going to take the root, and our answer comes out to 20.8 meters per second is velocity. Sorry, I had to squeeze in there. Okay, question 8 poses a different type of example, which is what if the object is moving at the start? So the best way to explain this is to show you a picture of what's called the Superman ride, and this is at Six Flags Magic Mountain in California. And Superman starts down here with what we call a launch start. Okay, so that means your kinetic energy initial is moving pretty fast. It's going to be a big number. So KEI, it's a big number. You're going to get launched up your coaster like this. Somewhere up here, it runs out of energy. It's going to pause for just a second. Okay, so that is your potential energy maximum, okay, which is also going to be your max height. That's probably what the question is going to have us solve for. And then you'll start to pull back down, fall back down on your own due to gravity. Okay, so how to solve any question like this? It's moving at the start, so potential energy initial is 0, and we're at the bottom. So that's our launch start. And kinetic energy final at the top is 0 because it pauses for a minute. So we can simplify our equation to kinetic energy initial here equals potential energy final, or your energy from your launch start equals your energy at the top of the ramp. Okay, now to solve for this, we are going to read our question and pull out our important variables. You're launched at high velocity, continue up the track until you stop, and then you plummet back down. The linear synchronous motor of Superman launches you at 160 kilometers per hour. Okay, so basically we should be thinking that's pretty fast. We're going to have a high amount of energy at the start of our ride. So to solve this, we need to turn 160 kilometers per hour into meters per second. So our shortcut to go from kilometers per hour to meters per second is to divide by 3.6. If we do that on our calculator, we get 44 meters per second. Okay, so we need to use that number, not the 160, as we fill in our equation. Our next step is to find our kinetic energy at the bottom of the ride and our potential at the top, but we're not given a mass. Okay, that's going to make things a little more challenging, but now we're going to do a little bit of fancy algebra called substitution and canceling. So My equation has kinetic energy initial here, which is 1/2 mv squared. I know that equation. And then on this side, I have potential energy final, which is mgh. Okay, both sides have an m. That means I can cancel them. So this m and that m will actually cancel themselves out. And then we can have a much simpler equation with no number for mass. So we'll do that on the next page. Started our equation here. And now we're going to do our algebra for this equation. So I'm going to fill in 1/2. My velocity was 44 meters per second squared. Gravity is 9.8, and height is what I'm looking for. Just a reminder, if you need to have a refresher on how to get kilometers per hour to meters per second, see myself or Mr. Crouch when we're back in school. In the meantime, in grade 10, you can just use a shortcut, and in grade 11, we'll show you the long way so that you know how to do it. Okay, the first part I'm going to do is square 44. So 44 squared divided by 2 on my calculator comes out to 968. Equals 9.8h. Now I'm going to divide by 9.8. So divide it by itself to cancel, divide by 9.8 on the other side, and h is equal to 98.7 meters. Okay, so we've done up to number 8 for part 1 of the video. I will do part 2 of the video with number 9 and number 10. Right now, at this point of this video, you can try the worksheet part 3. Probably numbers 1 through 8 are things we've covered. I'm going to show you what the worksheet looks like, but you'll need to download it from the website. Okay, so this is what we're talking about, conservation of energy part 3. And you can find that on the Weebly website. And for this portion of our video, I'm comfortable with you trying numbers 1 to 8 as a start. Okay, we'll see you at part 2 of the video.